Well, thank you for having me, and thanks for attending my talk. I'm Scott Noble. I'm from the University of Tulsa, and this is when I was making this slide, I started from the slides from last year, and I noticed that there was a sharp gradient in the population of our group. So we're really excited by the larger population of postdocs and grad students that we have working on this project. So we're really anxious to utilize this person power to do great things. And we hope with Blue Waters and the current status of our work that we're going to be doing really superb simulations, and hopefully we'll have a ton more to present to you next year. So, but there's still a lot to present this year. So the basic project I'll be focusing on is this binary black hole accretion problem. So in the previous two talks, you saw these superb simulations of developments of galaxies and how they develop nuclei, quasars, black holes, supermassive black holes at their centers. Now imagine they form two, okay? And then they form a binary, and they're in this dense core of the galaxy with lots of gas, and they're accreting this gas. And so we hope to observe these observationally through electromagnetic waves, but we also hope to observe them through gravitational waves with space-based gravitational wave interferometers like LISA. And so with that dual band multi-messenger sort of observation, we can really understand these objects in a really detailed fashion. And so this is that's the principal goal of this project. And so this visualization shows the magnetic field strength in the plane of the orbit with magnetic field lines emanating from each black hole. And Mark Van Moor has been really instrumental in making these visualizations for us, and he's helped us learn how to make them on our own, not quite as well, but we're really appreciative of the collaboration we've had with various members of the NCSA Blue Waters team. And also, besides the person power, we also have enough funding to support that person power in our efforts. So this is really coming with the SUs, the person power, and the funding. We're really in a good sweet spot for unique results. So we had two topics of focus in our PRAC. And one was the tidal disruption event simulation. So the idea was to see how bare black holes start accreting. So imagine you've got, a black hole is pretty boring. It's just parameterized by its mass, spin, and charge. Charge is usually irrelevant, but if there's no gas, you can't see it. And so that activity can be ignited if a star comes too close and gets ripped apart and disrupted. And so that can reignite activity of the nuclei, and we can understand how accretion develops. And Sasha introduced this topic really well, and so I won't go too much into that introduction. Specifically, also, we don't have much results to show on this topic. There was and so I'll be focusing on the results from the binary accreting problem. So these are exciting because they are LISA sources. These are laser interferometer space-based gravitational wave sources, so low frequency gravitational wave sources, not the sort of sources that LIGO would measure, but so LISA is going to be maybe launched in a few years, maybe 14 years. And so we have now ample time to predict what their electromagnetic emission would be, so that we can then search for them in the gravitational wave band, but also understand them in both messengers. And so this is pretty much a new simulation problem, and we're kind of leading the effort in simulating these things in a very realistic fashion. So we want to eventually start with these galaxy simulations which form binaries, and then we want to start them in the Newtonian regime, and then have them evolve to the post-Newtonian regime, which is where our simulations start. And then they will inspiral, the black holes inspiral because they release gravitational wave energy and angular momentum, and that allows them to get closer and closer together, and then they eventually merge and create a burst of gravitational waves, but they will also make a burst of light. And so that that coincident signature can help us both detect them, but also extract strong field gravity physics from them. So we can learn a lot about the strong field limit of gravity from detailed observations and simulations of these objects. And they're also, these two objects are both great sources for transient astronomy. So they're a prime target for all-sky surveys like LSST, PanSTARRS, the Catalina real-time survey. So that's why we kind of put them all into one package. But they're very different projects. And as I said, we're looking at the accretion problem in the post-Newtonian regime. In fact, we actually match perturbative solutions of Einstein's equations in different domains all together so that we can simulate from the wave zone all the way down to the black hole event horizon. Okay, so we're resolving black hole event horizons, and we're doing MHD on top of this dynamic space-time. And we use the code called HARM 3D to do this. And so before we do the full 3D problem, we thought it would be best to conserve resources, learn a little bit about the physics going on, and do this in the 2D hydro case. So we still are challenged by the large range in dynamic time and space scales that we have in the problem. We have to resolve the event horizon and also evolve it for long enough that the disk relaxes. And so this was a very challenging problem, even in 2D. And however, we were the first to do this in the post-Newtonian regime, and we were able to see the transition out of the Newtonian predictions that have been made a long time ago by Paczynski, and we saw how that prediction broke down in the relativistic regime. And we found that as the binary got closer together, the gravitational potential between them got shallower, and you could collect more and more matter in between the two black holes. And this sloshing region, which is this dashed square region here, you could collect more matter there, and that could be a source of bright electromagnetic radiation. And this variable signal then is characteristic and not easily derived from the orbital dynamics. So this is a result that you would only get if you did the dynamical simulation with all the physics ingredients. So there's this characteristic signature in the mass in the sloshing region that occurs at twice the orbital frequency, which is because this is an equal mass binary. So it's symmetric. So all the variability is tied to the orbital dynamics of the binary. But then there's also this power at 2.6 omega binary. And so this is actually material that reflects off of each of the mini disks. And it's a non-trivial dynamical effect that we found. So this could be, if we found an electromagnetic signature that was periodic, we could then tie it back to this predicted phenomenon that we've simulated here. So that would allow us to elucidate parameters from that binary using our models and those electromagnetic observations. So that was why it really mattered to do the simulation. And we were able to see how the Newtonian predictions broke down in the relativistic regime. So we also wanted to test the 2D simulation, also allowed us to test this novel initial data prescription. So we want to start with these mini disks. So imagine that there are these two disks of gas around the two black holes, but then there's an outer disk around them, right? So you imagine these two black holes immersed in this big cloud of gas. And so it's accreting this gas from this outer disk, but then around each black hole there's another disk, okay? And these are those mini disks around each black hole that I was talking about. But then we're going to immerse them in this circumbinary disk, okay? And that's basically what we did in this 3D MHD run. So we had simulations where we excised the volume around the binary, and that allowed us to evolve the circumbinary disk for a long, long time. so that it relaxed to a steady state. And because we want to evolve it long enough so that all the transients from the initial data decay away, and then we get something that is realizable in nature. And so we did this. So we had this circumbinary data from previous years running on Blue Waters, and we wanted to now look at what the accretion picture was near the black holes themselves. So we started with an initial set of mini disks around each black hole, and each one was like the disks that Sasha uses. So they have, around each black hole, there's a torus of gas that is threaded by a weak magnetic field. And we then let it rip, okay? So right here, there's this artificial cavity that we start with, which is totally fictitious, but we anticipate it'll quickly fill in due to pressure gradients and magnetic field gradients. And I'll animate this in a moment, and you'll see that, in fact, it does, and there aren't any long-term transient features that are apparent. So this is kind of a first-of-a-kind sort of calculation, so we're kind of treading on new territory, and this is all kind of R&D work that we're exploring with, and it seems to be working out, and we're being careful with everything. So we're kind of motivated that by these results that we're doing things correctly. So these are also, I just want to also point out that these are intermediate-sized runs. They're only using 600 nodes, but they have to run for a long time because we have to run because there's a large dynamic range in time, and we have to run long. So it was hard to fit into the queue because the queue prioritizes large jobs, and so we worked with David King and Jing Li to use a reservation, and they helped us set that up, and that was very beneficial, and we thank them for all their effort on it. So here we go. So you quickly fill in, and we orbit for about 1.5 orbits. And also notice that we have to, also to afford these simulations, we have to cut out the innermost a sphere about 2m in radius. And we use an absorbing boundary condition there. And unfortunately, that's what we have to live with until we develop this patchwork code that I'll mention in a few minutes. But so on the side view, so here we have a picture of this mini disk, but the previous one was face on, okay? So we were looking down onto the orbital plane. Now we're looking in a plane edge on to the disk, okay? So we're doing a cut vertically, and we're gonna be following that black hole as it orbits around. Okay, so you can see that these mini disks will go MRI unstable, and it connects pretty smoothly with the circumbinary flow. So what we're going to be focusing on is how those mini disks interact with that circumbinary disk, and to see what sorts of electromagnetic signatures we can take from these. So that was work in progress, so we're still analyzing the data fully, and we hope to publish it soon. I also want to say that some of our collaborators at RIT are doing gravitational wave modeling, so they're doing vacuum simulations without any matter. So it's just numerical relativity evolutions of binary black holes, and they're using these to generate gravitational waveforms to be used in the LIGO analysis or algorithm library that they use to do match filtering to detect sources, gravitational wave sources with LIGO. So this is really important work. I hope everyone is familiar with those gravitational wave events that have been detected over the past year and a half, and LIGO is expected to detect even more. So part of our PRAC is being used to generate these waveforms so that we can detect more and more of these sources. And in particular, two of these events were simulated using the RIT code, so on Blue Waters. And also, this patchwork code allows us to get rid of that cutout at the origin, but it also allows us to do the tidal disruption event simulation. If you recall in that movie, we had that really small star come near the black hole, and so in order to resolve that star, we need to cover it with a patch that is moving through on top of a global patch. Okay, and so that's a general idea. So here, particularly this test case scenario, has a square Cartesian patch embedded in a spherical global patch, okay? And we compare that to a simulation with just a uniform Cartesian patch. And we did a set-off Taylor blast wave test to see how the inter-patch transition worked, and it seems to work pretty well. So here we're comparing the X's, or the single patch, Cartesian patch run, compared to the global and local solutions. So the local is the smaller one in this multi-patch run. And so you see that here, particularly this transition between the local and the global is smooth. And any differences in the resolution of that shock are due to the different resolutions between the outer spherical patch and the single Cartesian patch run. So we're confident that through our other tests that this seems to be working. And the interpatch communication is all done through ghost cells. We also explored the scaling. I won't go into this. This is kind of a busy slide, but as we scaled this up to about 1,000 cores per patch, the communication pattern became only significant at that level. So if you went above 1,000 cores per patch, the communication load became significant, but below that, it was not significant. And that is encouraging because we're using a pretty naive algorithm to do that communication pattern handling. So I think if we do more intelligent communication pattern design, we can get this scaling performance even better. So this is in the works, and like for instance, an example of using this multi-patch code is to, instead of having, I didn't go into this, but if viewers at home see my previous talks from previous years, we developed this warped grid that allows us to pinch cells near the black holes in our binary disk simulation. And instead of using that warped grid, we would use this multi-patch code, or this patchwork code, to lay out different patches around the black holes, and also a global one to resolve the circumbinary disk. So we hope to get this working with MHD in our binary black hole accretion disk simulation soon, and use them in the next year. I also want to advertise that we've been working with Mark Van Moor to visualize our simulations, and he presented this at a Exceed showcase, and he's also been helping us with educating our students at RIT to learn these tools and to learn modern cutting-edge visualization techniques with Visit in particular, and they have been using Python code to interface with Visit and to track the camera, to move the camera around, and also to visualize the field lines that come from the black holes. And tomorrow, if you're interested in our load balancing project with AMPI, please attend my talk. I just want to advertise it here. We have a paid project that we're working with the Sanjay Kale's team, the University of Illinois, and pretty much in conclusion, I just want to say we're really excited about next year and continuing our mini-disk simulations, and we're confident that we can do really great things with the people we have, and we just need maybe we need all the SUs we can get now, and I want to thank Blue Waters for all its help, all of its support in a number of ways. But I also want to give you a little teaser trailer of the time-dependent radiative transfer calculations we're now doing with the mini-disk simulations. So here you see that the two black holes, this is in the plane of the binary system, and you can see the relativistic light beaming effects from the strong field gravitational curvature of the binaries. So thank you.